All right, guys, so we're going to go over a couple of questions. This will be our first one. We've got a rail truck of mass 4,500 kilograms moving at a speed of 1.8 meters a second, which is going to collide with a stationary truck of mass 1,500 kilograms. Okay, they're going to couple together, and what we want to do is calculate the speed of the trucks after the collision. Okay, now the first thing we need to do is decide how to solve this. Could be, we've learned several things so far. We've learned about SUVA, conservation of energy, constant momentum. There should be a couple of clues here that will tell us what we want to do. Number one, we're talking about a collision, right? They collide. Okay, given that it's a collision, chances are we're going to be looking at momentum. Remember that during a collision, we have sound, we have deformation, we have lots of other things happening that cause us to lose energy. And if the energy is being changed, then we can't really do conservation of energy. We're losing it to those other things. So it's likely we're going to do momentum. What kind of confirms that fact is that the trucks couple together, which means it's not an elastic collision, right? An elastic collision is one in which the kinetic energy is conserved. But in order for it to be elastic, they have to completely bounce off of each other and not have any linking or deformation or anything like that. We assume that it's not elastic unless we're told otherwise. All right. So what we're going to do is we're just going to go straight into conservation momentum. So we got sum of the momentums initial needs to be equal to the sum of the momentums final. Okay. So we'll go ahead and add those together. So I've got the momentum of the big truck. So that's my 4,500 kilogram initial plus the momentum of my small truck initial will equal the momentum of the big truck final plus the momentum of the small truck final. From there, I'm ready to start putting some numbers in. All right. Notice that I went ahead and wrote it out and made sure I have everything available. Then I'm going to start putting the numbers in. So we know that momentum is the mass times the velocity. So the momentum of the big truck initial will be its mass, which is 4,500 kilograms, and it is in SI units, so I can leave it the way it is, times its velocity, which is 1.8 meters per second, which I don't need the meters per second, that's also SI. Then we'll go plus the momentum of the small truck. We recognize that the small truck was stationary. Because the small truck was stationary, then it's going to have zero velocity, and zero velocity means zero momentum. So I'm going to go ahead and put in a zero momentum there. Now we're going to do the momentum of the big truck final. So again, it's 4,500 for its mass times its velocity, which we don't know, plus the momentum of the small truck. The mass of the small truck is 1,500, and we don't know its velocity either, but because they're coupled together, they're going to have the same final velocity. Now, some people here, and this is fine, some people here say, oh, well, if they're linked together, then really they're all the same object now. So that linked object now has a mass of 4,500 plus 1,500, and that object now has a final velocity of VF. You'll notice that that's going to end up giving you the same thing. Okay, so if that's what you did, that's fine. Just want to show you that. You may see that in a textbook or something like that. Or on the IB exam, sometimes they write it that way as in their mark scheme. So just so you see what's going on there. Okay, at this point, I'm ready to start plugging things into my calculator, which I have right here off screen. So I'm going to go 4,500 times 1.8, which is going to give me 8,100 plus 0 equals 4,500 plus 1,500 will give me, sorry, not 4. Man, must be in the morning. 6,000 times the final velocity, which is the same thing that we would have gotten right here, right? Add those two numbers, 6,000 times final velocity. So we go ahead and divide by our 6,000, and we get our final answer of 1.35. Please put the units on there. Meters per second is my final velocity. And there we go. We've answered the question. All right, let's go on. Let's look at another one. That was pretty straightforward. Whoa, I'm not quite sure what just happened there. Oh, let's see what we can come up with this time. All right, so this time, again, we have two railway trucks. We have a railway truck colliding with the stationary truck of mass 3,000 kilograms, first truck has some initial speed, and the second truck moves off with a speed of 1.9 in the same direction. Okay, so this time it's asking us for the velocity of the first truck immediately after the collision. Okay, now again, it's talking about collisions. If it's talking about collisions, we're going to probably assume that we want to use this idea of conservation of momentum. So we've read the problem. I'm going to minimize this a little bit. We're going to need a little bit more space. So here we go. Conservation of momentum. We know conservation of momentum is that the sum of momentum's initial need to equal the sum of the momentum's final. Okay? Now with that, we'll say we've got the momentum of the, again, we have the big car and a small car. So momentum of the big car initial plus momentum of the small car initial should equal the momentum of the big car final plus the momentum of the small car final. And again, I'm going to start putting some numbers in here. So the momentum of the big car initially, it tells us has a speed of 2.5 meters per second. So I'm going to put in its, remember, momentum is mass times velocity. So I'll put in my mass, which is 6,000, times its velocity. Notice again that both of these units are already in SI, right? Kilograms and meters per second. And so I'm okay just putting those numbers in. Plus the momentum of the second car. Again, the momentum of the second car will be 0 because its initial velocity right here is 0. So we'll go ahead and put in 0 for its momentum. Equals the final momentum of the big car, which at this point we don't know, right? That's what it's asking us for. The velocity of the first truck immediately after the collision. So we're going to go ahead and put that in as our final velocity, which we're looking for. Plus the momentum of the second car, which again is going to be 3,000 kilograms. We went backwards. Ooh, that was fun. Okay, velocity of the second car, 3,000, times its velocity, which is given to us. It tells us it leaves with a speed of 1.9 meters a second. And so at this point, we're ready to start working through and putting our numbers together. So 6,000 times 2.5 is going to give me 15,000 plus 0 equals 6,000 times the final velocity plus 3,000 times 1.9, which is 5,700. Okay, and then at this point, I should be able to start solving my linear equation, subtract the 5,700 to the other side, so minus 5,700 to both sides, and that will give me 9,300 equals 6,000 VF. Then divide both sides by 6,000, and I get 1.55 meters per second. Now, it's important to note here that the 1.55 meters per second is positive. That means that it's moving to the right. Okay? And that's actually really important because the question asks for the velocity of the first truck. Velocity, remember, is a vector. Because it's a vector, we need to give both a magnitude and a direction. If I were to get a negative number, then that means it would bounce back. You can probably kind of reason through that it's more likely if you have a bigger object that object is going to maintain its momentum a bit more or its inertia, and it will continue moving in the direction that it was moving before. If you have a smaller object, it's much more likely that it's going to hit it and bounce off, right? And so head in the opposite direction. So you can kind of use that as a rule of thumb. Just to kind of be able to reason through and say, well, what direction should it be? But your math here should always answer that question for you. All right? Now, the other question it's asking us here is it wants us to give us the loss in kinetic energy. Now, given that it's a loss of kinetic energy, we already knew we couldn't do conservation of energy. But to find the loss of kinetic energy, what we're going to do is we're going to find the initial kinetic energy, and we're going to find the final kinetic energy, and we're going to subtract the two, right? So to find the change, it's always final minus initial. Sorry, keeps doing that. So we'll go kinetic energy final minus kinetic energy initial, which will give me the change in the kinetic energy, or the loss. I should get a negative number there. So let's go ahead and find out, right? So kinetic energy, remember, is 1/2 mv squared. So I'm going to do the final kinetic energy, which is the kinetic energy of both objects. So I'm going to do 1/2 times the big mass, which was 6,000, times its final velocity, which we just found was 1.55 squared. And then I'm going to add on the kinetic energy of the small one, which is 1/2 times 3,000, times its velocity, which was 1.9 squared. So that, all of that right there is my kinetic energy final. We're going to subtract the kinetic energy initial. The kinetic energy initial is going to be the same, so 1/2 times 6,000 times its initial velocity, which was 2.5 squared. And the smaller car only had a velocity of 0, so that one we're going to leave the way it is. It's 0 kinetic energy. And so at this point, we should be able to plug that in. So go ahead, put it in your calculator, find out what you got. I'll see what I got. So when I did this, I ended up getting an answer of negative 6127.5, and of course that's in joules. Now, if I'm looking at significant figures, which I really should, these two answers only have 2 significant figures. So I'm going to go ahead and put my answer in 2 significant figures. You could probably argue that these only have 1 significant figure, but I'm going to go ahead and put it in 2 significant figures anyway. So my final answer is going to be negative 6100 joules. Okay, now because it's negative, that means that the final number, the final amount of kinetic energy was less than the initial, right? I did the final minus the initial. So that means that I lost 6,100 joules. All of that energy was lost due to friction, due to sound, due to, wherever else energy could go in a situation like this. All right? So there you go. That's the answer to this question.